second lecture of the tutorial on Replica-Exchange Wang-Landau sampling, which will be given by Ying-Wai Lee from the Oakridge National Lab. Thank you.
Thank you. Thank you for, I want to thank the organizer for inviting me to come here and give you actually 2 more lectures on the tutorial and also another talk tomorrow's morning. So this talk is actually the continuation of the tutorial on Replica-Exchange Wang-Landau sampling. The first lecture was given by Professor Landau yesterday. So today I will talk about the main algorithm of Replica-Exchange Wang-Landau. And on Friday, I will give you some more introduction to a programming techniques called the MPI, Message Passing Interface. And this is a, you can take it as a library that you can use to really write programming, write codes, write parallel codes with. So that will be on Friday. Okay. So I want to do a little bit of a review of a summary what David has talked about yesterday. So he gave a background and motivation for why we need better algorithms to do Monte Carlo simulations. For example, Metropolis algorithms are very widely used for the last few decades, but it has its limitations. And for example, it's very difficult to sample complex systems with complex energy landscapes. And so he also gave an introduction of a new algorithm called Wang-Landau sampling. Basically, it does a simulation on to obtain the density of states G of E of a system, or you can take this as the energy degeneracy of a physical system given the Hamiltonian. And from that, from the density of state, you can easily calculate all the thermodynamic quantities from a few formulas. And it is not the same as accumulating the ensemble averages when you do a Metropolis sampling. So the good thing about that is that if you run a Wang-Landau simulation and obtain the density of states, then you can calculate all these thermodynamic quantities at all temperatures from only one simulation. Of course, in practice, you should not do only just one simulation because you need error bars. So this lecture, I will give a background and motivation for why is it still not enough to have Wang-Landau sampling, because we want to parallelize it. We want it to run even faster. So that's the motivation behind why we need more parallel Monte Carlo algorithms. And then I will give an introduction of to the Replica-Exchange Wang-Landau sampling. I will also talk a little bit about how to speed that up. There are a few parameters you can tune within the algorithm, and how to look at the performance. And then finally, I will give a few examples of how we are applying Replica-Exchange Wang-Landau sampling to real-world material science problems. So just a very brief review of Wang-Landau sampling that David has already explained yesterday. So we start with an initial guess of the histogram that keeps track of how many energy visitations of the energy levels of the system. And then we also have an initial guess of the density of state, and a very simple guess is that it doesn't have any energy degeneracy. And the initial modification factor, which is for modifying the density of states later on, we set that to e to the power 1. And this can be any values. It's just conventionally we do the same as the original Wang-Landau paper, but in principle, you can set any values you want, which is greater than 1. Just like any Monte Carlo simulations, you generate child configurations, and then you accept that with a probability, which is inversely proportional to the instantaneous density of state. And let me remind you that this density of state keeps changing within your simulation. So, yeah, and then and another very important point to note is that, like metropolis sampling, if you have if you accept the new energy, then of course you do the update with the new energy. But if you reject the trial move, you have to return to the old configuration and do your update with the old energy. So how to do the updates? We will modify the density of states with the modification factor. So you see that because this factor is greater than 1, you always increase the counts of the density of states. And then you count how many times you visited this energy in a histogram. And you repeat these 2 steps until we obtain a flat histogram. And there is another factor we have to consider here. Usually you take the histogram to be flat if all the entries in the histogram is no less than a certain factor of the average of the histogram. If the histogram is flat, then you reduce the modification factor, and then you repeat all these steps until a predefined value is reached. And usually we take this as 10 to the power, at least 10 to the power minus 6, and a better estimation will be, or better answer, better conversions will be obtained if you further, well, do more iterations after that. So the final product you will get out from Wang-Landau sampling is the density of states G of E. So far so good. This is the serial scheme of Wang-Landau sampling, which you can do with your laptop, with your cell phone even nowadays. So what is the problem? Or what is good or bad about serial Wang-Landau sampling? Of course, the good thing is that it's very simple to understand. It's very simple. Well, I will not say it's simple to understand, but it's simple to implement. It's simple to implement, and it's very robust. You can basically apply this to a lot of systems besides speed systems. And for example, for my PhD study, I apply this to protein folding problems. It's also possible because Wang-Landau sampling is so general that it doesn't depend on the form of the Hamiltonian of the system. So very importantly, it's independent of temperature. So we don't have to repeat the simulation at different temperatures if we want to have obtain the thermodynamic information of the system. You can just do one simulation for all the properties at all temperatures. The bad thing is, of course, sometimes you cannot tell how long it takes to simulate, to finish the simulation. And it's serial, so you have to wait. You really have to wait until the entire procedure has finished. So that motivates us to think about ways to speed that up, or how to put this on some workstations if you have more than one CPU or more than one nodes to use. So a very naive way, so a very naive way to think about this is that, well, we have the density of state, and we want to simulate this. How about we put multiple walkers, multiple random walkers, and then we update this same density of state, with multiple walkers. And here, then you can use one CPU for one walker, and then you communicate, and then you update the dense of state. So a former student of David has done this before, and he discovered a problem with this scheme. If you look at this is the time series of the walkers. That means if you plot which energy a walker has visited during the simulation, and you plot multiple of them with different colors, you see that at some point, some walkers got trapped at some low energy levels. So the reason is that because some system, your lower energy states are so hard to discover during the simulation. So they are not discovered at the very beginning of the simulation until later. And when they discover these lower energy states later, the walker spends a lot of time to catch up, to build up the histogram and to build up the dense of states. And that's the problem, because even with these, they catch up with the histogram, they catch up with the dense of states. If you look at the final answer of the dense of states and compare that with the serial Wang-Landau sampling results, you see there is a discrepancy here, basically for any state lower than certain energy. So then, with this, you can understand that with these multiple walkers, single histogram scheme, you do not get correct statistics at low temperature or low energy states. Yes. Yeah. So yes. So the problem is this: with 1,000 walkers, they can do things much faster, but they can also visit those states which are easy to visit, much easier and much faster. So it's much harder for example, 998 walkers are doing the simulations, doing the sampling at the high energy region, and it's very hard for example, the 2 walkers to catch up with what has been updated by the rest of the system. The one walker is not exact. Well, yes, I would say yes, but at least this problem is not as severe. And yeah. 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 Oh well. Not the same. It's just that we carry the simulation until the modification factor is small enough. Yeah. So yes, the problem is here because most of the workers are updating this region, and they build up the histogram very quickly, and it's very hard for a few workers to catch up and build up the histogram from scratch. Yeah. So this is the problem. All right, so then now we know that the first scheme is not working very well. So we need another scheme. So another scheme is that, well, what if we have multiple walkers, and then each walker has its own dense of states and histogram? And so here we don't have the same problem because each walker has its own histogram, so it is not really affected by other walkers. It just updates its own histogram, and then from time to time, you exchange you exchange the configurations, just like what you do with Replica-Exchange or parallel tamping. So from time to time you do this, and then when you reach the end of the iteration, you still need to combine all these dense of states, do an average, and then redistribute that again, and start another iteration. Yes? Can you repeat the question again? Yeah. Yes, and this is like, yeah. Yes. Why do I get what? Flat? Why do I get trapped? Ah, okay. So the problem is the same as this one here. It gets trapped because it spends a lot of time on that in that low energy regions. So it doesn't get trapped anymore after it has caught up with the histogram and the dense of state. But at the very beginning, when a new energy bin is discovered, it needs to catch up with the others first before it will not trap the random walkers anymore. So what I meant by getting trapped is just a momentarily effect when the energy bin is first discovered. It's only the first time when it's discovered. And on top of that, if the simulation has already go on for a while, because then you can imagine that this problem will happen. You will build up the histogram and the dense of state, and they are very large. The values are very large for other bins, and the newly discovered energy bins are 0 basically. So you need to catch up with that first before your random walker can go out. So this is the problem. This is why it gets trapped. Okay. So this is basically the basic. Well, let's go back. So these multiple walkers having its own histogram and its own dense of states is the basic for Replica-Exchange Wang-Landau sampling. But here we do something a little bit more sophisticated, just like what David has introduced yesterday, that in the very early time when they first started to parallelize, or the simplest parallelization of Wang-Landau sampling, without running it parallelly, you basically have one CPU taking care of a smaller energy range. And we are doing the same thing here, but this time we are running all these random walkers with different energy ranges at the same time, and occasionally they communicate. So how we do that? Let's say we know the entire energy range already at the beginning, and then we divide these entire energy range into a few smaller ranges. And then we run the Replica-Exchange Wang-Landau sampling with these smaller energy ranges, but they need to overlap. So you cannot chop them into into pieces that they don't overlap, because we need the overlapping for the communication later. And then you just do normal Wang-Landau sampling within the walkers, within one energy window. And then from time to time, we have to exchange the replicas. How we do that? So let's focus on the first two windows. Let's say the first window, I have the tensor of state G of E, I mark this as GI of E. The second energy window, I mark this as G of J of E. And the configuration at a certain point, when I freeze the entire scheme, the configuration is X for the first histogram, and then is Y for the second histogram. So we look at these two energy states, and then we ask, how do I know I should accept this or not? So in a Monte Carlo simulation, we look at the acceptance probability. Here, we also look at the acceptance probability, but with a little modification. So if you look at this sum, we have to include a term from the first histogram. And if you recognize this, this is very similar to the acceptance probability in Wang-Landau sampling. Remember, in Wang-Landau sampling, we have the ratio between the tensor of states of the old state and the tensor of state of the new state here. So this is basically it, because if you look at the first histogram, if I propose a new move Y, and this configuration Y is a new configuration to the first histogram, the first Wang-Landau sampling. So that's why this is in the denominator here. And then, so the first term, the first ratio here basically is the acceptance probability for the first window. And you do the same for the second window. But this time, configuration X is the new configuration to the second Wang-Landau sampling walkers. So that's why this time is the tensor of state G of J of the configuration, the energy of the configuration X. So this is how we write down the acceptance probability to make sure detail balance. So once you look at that, and then if you decide that is, you throw a random number, of course, and then if you decide to accept that, then you exchange your configurations. And here, actually, you can exchange something which is the smallest. I can talk about this later in the details. But for example, if your configuration is too large, if you have 1,000 atoms in your simulation, it takes much more time to exchange the configurations. So then, in that case, you can also exchange the histograms and the tensor of state instead. And it's also possible. So it depends on how large your system is, how much communications you need. And depending on that, you can decide whether you want to exchange the configurations of the system and or the histogram or the tensor of states. Yes?
Just because the energy range of those two windows are not the same, then you change only part of the histogram and I mean, because since the ranges are different.
You exchange it and you exchange the entire thing. So you exchange, I can imagine that you store the histogram in an array, and you exchange the entire array.
But the range of energy is different.
The range will be different. Yeah, the range will be different. But it's okay. So it's like I'm CPU number 1 here. Originally, I'm responsible for this range. And now I have to be responsible for this range instead. But I just do the same thing later on. Yes. Yeah. What do you mean by smooth? You just do the same. It doesn't matter whether your energy landscape is smooth or not. Ah, okay. So it's actually not dependent on whether your energy landscape is rugged or not. It's not related. It's just that, I can show you the next slide. So it's just that so the case you're talking about is something like this. If, for example, I have this configuration which is out of the range of the other energy range. So in this case, you just don't do the exchange, but just check the energy. You just check the energy and see whether the energy is within the energy range of the others. So it's actually the same when you do serial Wang-Landau sampling, that if you go out of the energy range, yeah. Yeah, well, if it's the case, well, actually, you can, it's still not, it's still, I still don't, I'm not convinced that if you have a rugged energy landscape, you go out of the energy range more. But the thing is, we sometimes also will have, will intentionally put in some global moves so that your current energy differs a lot from the previous energy. So this we do also. And the reason for that is exactly to bring the system out of some local minimum, and then you have a better sampling. But anyway, in the case so we can discuss this later, that whether it's related to the whether it's related to the energy landscape. But in any way, if you go out, if you generate a new state which is not inside your energy range, you just reject that, but you count your old state again. So it's just like the normal. Yeah, well, but this is also something you can tune. This is something I will go to that later. And you have a question? Yeah, I see your point, because then it corresponds to a probability distribution. Yeah. Well, so that's why I think this is the way we set the energy range is not so naively evenly distributed. Yeah, so I will come to that later. Yeah, so basically here I want to just point out that there are some generalization here. For example, you can run multiple walkers where they have the same energy range. Several of them has several of them has the same energy range. Or we can also do something like this, exactly like how you set the temperatures in your parallel sampling. So here we can also do something like this if we want to have better resolution on some of the energy range, that might be corresponds to certain temperature that you are interested in. So, well, so just to give an example of how well it works. So a few years ago, I was studying the HP model for protein absorption, and so this is the 67mer that I studied, and I cannot finish the run by only using the serial Wang-Landau sampling. So, but then the Replica-Exchange Wang-Landau sampling, with that I can finish that, and then we measure the number of Monte Carlo steps needed, and it's actually fewer. The number of Monte Carlo steps are fewer than the zero Wang-Landau sampling. And so when we measure the speed up, it's nearly, we get a speed up of 20 times. So, and the reason is this a little bit. Because at the very low energy region, there are some holes here, and you see the density of state is quite rugged here. And we really need to focus on just a small energy range to get all these states correct, and then we join them together. So this is a little bit of the reason. So Thomas Vogel, he's now a professor in University of North Georgia. He has done these two experiments. One is on lipid bilayer model, and then one is on the 10-state pulse model. And he shows that you can obtain quite nice, strong, and weak scaling with Replica-Exchange Wang-Landau. For example, if you just divide the energy range into equal pieces, then you get a speed up like this with the blue dots. You already get a speed up, but it's not as nice as the linear speed up. Linear speed up means that if you employ n CPU or n processors, your run should run n times faster. So this is the line that we draw. So if you get a linear speed up, that means you get n times faster. So it's not as, so if you divide the energy range into equal pieces, it gets a speed up, but not as nice as the linear speed up. But then if you do the runtime balance way to chop the energy ranges, so that is the second case I just showed. Your energy ranges are not the same size, but you chop it in a way that at higher energy region is easier to sample than to give it a wider energy range, and with the lower energy region is much harder to sample, or the transition is about some temperature, and you reweighted that and see, this corresponds to this energy range, and you give the energy range more attention there, so you have a smaller energy range at that energy region. So if you do this, then actually you get a very interesting speed up behavior. You can beat the linear speed up. So that means this is actually happening for me as well. Before, I was using 9 processors, but I can obtain the results 20 times faster. So this is that's why it speed up my simulation tremendously. And this is also the case for the lipid bilayer model. And yes. Yes. So yeah, we make a pre-run. Yeah. And then we make an estimation. Yeah, roughly. Yeah. So okay. So for the 2D 10-state pulse model, Thomas gave a measure of the weak scaling. So you can see the difference here. So for example, within a few hours, you can already simulate a system size which is as large as 300 times 300, where with 0 Wang-Landau sampling is not possible to do. Okay, so the next question we ask is, of course, so, well, how can we quantify all these speed ups? And we thought about 2 ways to measure it very intuitively. For example, the first measure we are thinking about is the wall clock time. For example, you sit down in front of a computer, watch it to wait for it finish, and then how much time is gained. So this is approximately proportional to this sum, where you can count the number of Monte Carlo steps needed in the 0 run, and for your parallel run, of course, you have to wait for the slowest walker to finish. So then you can count how many Monte Carlo steps is needed by the slowest walker in your set of CPUs. So this is the first measure we looked at. And then the second one is a little bit different, but it's also relevant. So if we look at the total computational effort taken by the zero Wang-Landau sampling and the parallel Wang-Landau sampling, we can also ask, so what is the total number of Monte Carlo steps compared to the total number of Monte Carlo steps by all the walkers add together? So this is the second measure we are also looking at. So here we take this as the algorithmic speed up, because you can also imagine that most of the case, actually what happens is that with a parallel run, you do mostly more Monte Carlo steps than the zero one. But then is it possible sometimes to even reduce the number of Monte Carlo steps so that it's more efficient than the zero Wang-Landau sampling? And so this is really what is gained by changing the algorithm, as opposed to if you just divide a large number of works to parallel walkers. So yes. What is the difference of? Percent difference of what? This is just difference. This is a percent difference. Well, in essence, it's the same. Yeah, in essence, it's the same. Okay. So one more slide, and then we can look at some performance results. So in fact, these two speed up measures I just introduced, they are related to each other in a way that the first speed up measures, which is the wall clock time, again, is related to the second measures, which is the algorithmic speed up, by a factor of n, because you are employing n walkers or n CPUs to do the parallelization. So yeah, so this is just what I said in words. So what you can think about is, so if you look at the second speed up factor, this is the algorithmic speed up. So if this is 1, that means I need the set of Monte Carlo steps to finish my simulation. But then I divided this into, I divide the entire effort to n walkers to do, and that's why I should get n times faster. But in principle, if I only get the second speed up factor as 1, then I only gain my computational time by splitting up the effort. But if we can, for some reason, tune the speed up factors to be greater than 1, then this is really what we want, because of a new algorithm, and it takes fewer total Monte Carlo time. So that's why we look at both measures. So here is some measures that we took, and we have several ways to optimize the algorithmic speed up. So the first, I have already mentioned, we have to adjust the window size carefully. And one way we did was that we finish, if they finish the iteration roughly at the same time, then we take that energy range. And yes. Okay, all right. Okay, so these are already shown. It's a work measured by the lipid bilayer model. Yep, so what we did was basically this scheme. So another thing we are measuring, we are now comparing the two speed up factors, and you can understand the scheme a little bit better here. So another way to, another thing to tune is the number of windows you use in the Replica-Exchange Wang-Landau sampling. So you can use 7, you can use 9, or you can use 11. But but how does it? So which one should we pick? And this is something I would like to see. But in this plot, we cannot see this yet. But at least we see the behaviors. So for example, if you look at the first speed up factor that tells you how much wall clock time you have saved. So you see that if you employ more sub-windows in your sampling, of course you finish the simulation much faster. But the scale is roughly n to the power 0.5, minus 0.5. So basically square root of n. So if you have n CPUs to do the parallel run, you get a approximately root n speed up. But then actually if you look at the total computational effort, it goes as n to the power 1/2. So at the end, we actually do more work. We do more work, but then we just distribute this to n processes. And so at the end, you still get a total speed up of root n. But then from here, the second graph, you see actually the total Monte Carlo steps needed are more. We need more. Well, so it's not very satisfying. So another thing to look at is the Replica-Exchange frequency. So another thing we can ask is, so we do normal Wang-Landau, we do 0 Wang-Landau within one small energy range. But then how often should we do the Replica-Exchange? How often should we communicate? And if you look at that and try the Replica-Exchange frequency after several steps, so you see that now for some cases, you can really get the speed up factors greater than 1. That means if you exchange enough, if you exchange frequent enough, then you need fewer Monte Carlo steps than the 0 Wang-Landau sampling. And then on top of that, you distribute all these steps over to n parallel walkers. So you'll get a total speed up much faster than linear speed up. And this is actually the reason why we get super linear speed up in our scheme. So, but then of course you can see if you do this too frequently, it doesn't help. And if you do this exchange not frequent enough, it also doesn't help. So there is an optimal Replica-Exchange frequency here. And this is very different for different problems. So basically, this is something that you have to play with and experiment with when you have a new physical system to study. Okay, so here is the basic Replica-Exchange. Yes. Yeah. Yeah. So now you're breaking this up into windows. Yeah. Using each of the windows, and then at certain time intervals, you switch between those. Yeah. So you're adding another level of dynamics on top. Right. And if you do that right, then you get a speed up. Mm-hmm. But in a sense, that is kind of throwing the whole flat histogram idea over the grid. Right? So then why use flat histograms in the individual windows in the first place, and not try to tilt, for example, in order to get a speed up? Ah, tilt the histogram. Like the entire histogram. Ah. That once you reach what you want to reach, everything becomes diffused. Right? And now you're solving that problem by cutting it into pieces and adding another That's a very interesting suggestion. Well, we haven't tried that, yeah, but yeah. So yeah, let me think about this later on because it's really interesting. Um, but I'm thinking something like, so why do we not do this in, for example, um, multiple MUCA in multi-canonical sampling? Is because, well, we basically want to have the histogram flat. That means we want the phase space to be equally sampled or equally well sampled. Where if you tilt the histogram, you impose a bias. You impose a bias, and then basically then there are certain area of phase space that is less well sampled. Yeah. Right. Yeah, these are two different things. But here we have speed plus a correct sampling. Yeah. Yeah. Yeah, I think so. Yeah. Right, yeah. Yeah. So actually yeah, yeah. I think that will work actually because tomorrow I will talk about something new. It's a new algorithm, not Replica-Exchange Wang-Landau, but the idea is very similar. I basically tilt the histogram not in one direction, but individually. So yeah, I think your suggestion will work. Yeah, so we can discuss more after the talk, but it's very interesting, yeah. Well, so in the last few minutes, I want to show you just some applications we are doing with the Replica-Exchange Wang-Landau sampling at Oakridge. So at Oakridge, we have a supercomputer with GPUs, and is now I think maybe the fourth or the fifth fastest in the world, but it's still the fastest in the United States. And this is just a computer, well, not just a computer, but it's a computer like a basketball court size, and my office is just on top of that. But then, of course, I want to find ways to use as many CPU hours there as possible. So what I have developed after coming to Oakridge is a little bit of a sidetrack, but I implemented Replica-Exchange Wang-Landau in this code called OWL, Oakridge Wang-Landau, but now it also includes Monte Carlo algorithms that are not only Wang-Landau sampling. I have multi-canonical sampling, Metropolis, and will be coming soon will be the parallel tamping. So this is a code that we will make open source later in the year or maybe at the beginning of next year. So this is a package that includes a collection of Monte Carlo algorithms to study finite temperature materials. And right now it's user-driven. So whenever there is a user coming to me and say, we need this, and I will just code this up and so that the users can use. So the special thing about this is that we interface the Monte Carlo algorithms with external packages. For example, we have interfaced this with a lot of density functional theory codes. The motivation for doing that is that we want to have, we want to study first principles Monte Carlo simulations, as opposed to, for example, for MD, for molecular dynamics, there are already ab initio molecular dynamics that basically calculate the forces from density functional theory, and then you do the molecular dynamics. And here we are actually simpler. We don't have to calculate the forces, but we only need to calculate energies, and then we do ab initio Monte Carlo simulations. So this is the motivation behind developing this package, because this has an object-oriented design that decouple the Monte Carlo algorithms with the system and with the interfaces with external packages, so that you can plug in any libraries you want or any external codes you want to do the ab initio Monte Carlo simulations. But you can also do Ising model there, no problem. It's a C++ code, so you can implement any physical system you want and then just do the Monte Carlo simulations with the algorithms provided. So just a little motivation of how Replica-Exchange Wang-Landau is designed inside the code is implemented in this R code. And then we have an interface with different packages. And here you see this one blue rectangle here corresponds to a library call. So here you can use multiple CPU calls for example, calculating one energy for a very big system using a density functional calculation. So then, and I have a little more details here with the implementation, but that's okay. I think I can skip this. So the takeaway message here is that this is how we use Replica-Exchange Wang-Landau sampling, and then combined with some external libraries or some other things to really scale up to supercomputers. Even without the very complicated energy calculations, we can still do this with Replica-Exchange Wang-Landau. You can still parallelize your code on a workstation. So this is the main message I'd like to introduce. So just a very brief performance measures. We use 17% of Titan and use Replica-Exchange Wang-Landau sampling to study a nickel atom system. So we want to look at the magnetic phase transition where the Curie temperature occurs. So with a small system like this, we already have attained 2.5 petaflops with less than 20% of Titan. And this is already more than the Golden Bell performance when this code, this DFT functional, density functional theory code got the Golden Bell Prize. So this is what we are doing right now. And there are some other projects who are also using Replica-Exchange Wang-Landau code right now to do their science. For example, some scientists are trying to understand the ferroelectric phase transition by using Wang-Landau sampling and then combine this with quantum espresso. So they want to see the phase transition and see how it compares with experiments. And then another scientist is using this to study basically binary alloys and see how the caloric behavior is like and how, for example, the order-disorder phase transition is like. And all these are Monte Carlo simulations combined with first principle energy calculations, because at the end we want to be able to compare to experiment data. So these are work still going on, and I cannot talk too much here, but I hope, for example, in the coming year, these projects will have more scientific results to the public. So that's all about the algorithm, and on Friday I will talk about how to really do the programming, and I will talk about message passing interface, MPI a little bit, just enough introduction that you can start some simple coding and simple parallel programming, and then that should be enough for coding up Replica-Exchange sampling. Even if not, it will be useful for coding up some other parallel algorithms like parallel tamping, or there is a recent parallel implementation of multi-canonical sampling, that will be useful too. So if you're interested, go online and take a look at some introduction of MPI, and then I will have some demonstration in C++. So simple should be simple enough even if you are a Fortran programmer. So